Today, the UVM Register Layer. What is the UVM Register Layer? The UVM Register Layer classes are used to create a high-level, object-oriented model for memory mapped registers and memories in a design under verification (DUV). The register layer defines many base classes which can be extended appropriately to abstract read and write operations to the DUV. Before we are going into we are Before we go into details of UVM register layer, let's first review how registers are organized and how they function in a digital design. What are registers? Most digital design blocks have software controllable registers that can be accessed via a preferred bus. These registers allow the hardware to behave in certain ways when programmed with certain values. For example, there could be a 32-bit register with several individual fields within. Each field represents a particular feature that can be configured by software when required. The figure above is an example of a single register within the design with five different functional fields. Field properties may be specified by designer as below. The design files may have a module in RTL to implement these registers. What is a register block? There would be a collection of such registers where each register has a different set of field and configuration. For example, reg_clt could be placed at an offset address of X to emphasize that it is main control register for the module. Because it takes 32 bits, 4 bytes, the next register, reg_state, would be at 4x, uh, sorry, at 0x4 and hold the design status related flags. So what is a memory map? An SoC normally has one or more process core, DMA engine, and bus network interconnects and may prefer modules. Each preferred module would have an associated register block, and they are all laid out in something known as a memory map. Memory map is like a massive table that defines address ranges in the various memories and preferred device registers on a processor mode bus. The processor would have access to these register blocks through a preferred bus block like APB or Wishbone. So each preferred block would require a base address on which respective register blocks can reside. So let's consider the register block described above to be a part of the timer design module, which has a base address of 0xe7b30. In order to in order to access the reg_clt of the time block, the core would have to send a transition with an address of 0xe7b3 since 0000 or 4 zeros. Since reg_clt has a base address of set of 0x0, to access reg_dmxctl, the core would send a transaction with the address of 0x e7b3 underscore 000 plus oxc, because reg_dmxclt has an offset of oxc. The next is Register model. The UVM register model. We've already have an idea how registers are laid out in a memory map from introduction. So we will simply use existing UVM RAR, register abstraction layer, classes to define individual field, registers and register blocks. A register model is an entity that encompasses and describes the hierarchy structure of a class object for each register and each individual field. We can we can perform read and write operations on the design using a register model object. Every register in the model corresponding to actual model register in the design. There are two kinds of variable inside the register within a model. Desired value. This is the value we like to the design to have. In other words, the model has an internal variable to store a desired value that can be updated later in the design. For example, if we want the register leg underscore stat in the design to have a value of the OX1234 5678. Then the display desired value of that register has to be set to 1x1234 underscores 5678. Within the model, the update task should be called for this to be reflected in the design. So mirror the value. Every time a read or write operation occurs on the design, the mirrored value for that particular register will be updated. Hence, the mirrored value in the model is the latest known value in the design. This is very useful because we don't have to issue a read operation every time we want to know the value of a register in the design. The desired and mirrored values also exist for every register field. Creating a register class. Consider that we are building the model step by step, and the first logical step mo- would be would be to identify all registers in the design and create an object for each register. From introduction, we will first create a register class object for reg underscore cpl. Since each, each fields are already known, well defined. Every register object should be inherited from UVM underscore reg class, and every register field should be object of a UVM underscore reg field. Note that you don't have to create a separate class for a register field, but simply create an object for every register field as shown in the example below. The fields have been declared as rand so that they can be randomized when required and are of the UVM field. This is only declaration for all fields, and actual definition will come later on. Next, we have to write a new function as you normal do with any UVM class. The super core will require three arguments, with the first one being the name of the register. The second indicates the size of the register, which is 32 bits in our case. The last parameter specifies which functional coverage models are present in the extension of the register abstraction class. Until this point, we have not defined anything related to the register field, and hence, let's do the next in custom user function called build. We will keep the function virtual just in case someone else tried to override the method and call their own version of the build. The configure method is used to define the field attribute to the class object and has the following argument. In a similar way, you can define a separate class for each register in the design. Creating a register block. After all registers have been defined, it needs to be made a part of the register block. For this, we will define a register block that inherits from the UVM leg block and create an object of all register with it. For our purposes, let's put only three registers in this block. An object of a leg block class is a register model and can be used to access all registers and perform read and write operations on them. We have only covered the first part of how a register model is defined. The question of how the actual DUV will be written to and read from has not been discussed yet. To perform register operations, you have to send valid bus found transactions via a preferred bus, which will be covered in the next section. The next section is register environment. In UVM register environment, in register model, we have seen how to create a model that represents actual register in a design. Now we'll look at the different components in a registered environment required to perform register accesses, such as read and write operations. There are essentially four components required for a register environment. A register model based on a UVM classes that accurately reflect the values of the design registers. An agent to drive actual bus transaction to the design based on some protocol. An adapter to convert the read and write statement from the model to protocol-based bus transactions. A predictor to understand bus activity and update the register model to match design contents. And the register adapter. UVM has a built method called a read and write to initiate the read and write operation to the design. These register read write access calls create an internal generic register item of the UVM reg bus OP, which is a simpler structure as shown below. To convert the read and write method calls into actual bus protocol accesses, the generic register item is converted to a protocol-specific bus transaction, then by a component called an adapter. The adapter needs to be bidirectional so that it is able to convert the generic register items to a transaction and convert both transaction responses back to the generic register item so that it can be updated the register model. The conversion process is facilitated by the adapter by leg to bus and the bus to leg functions. As the name imply, as the names imply, leg to bus convert a register level object of a type UVM leg bus operate OP into a protocol transaction and bus to leg convert the bus level transaction to a register level object. Bus protocol vary between the design and hence a custom adapter has to be inherited from the UVM underscore reg underscore adapter to override the functions. There are also two variables in the chapter to handle byte enables and response times. The bit supported byte enable should be set to 1 if the bus protocol allows enabling certain byte enables to select certain bytes over data bus and as valid. The bit provides responses should be set to 1 if the target agent driver sends separate response items that require response handling. Since APB bus protocol does not support byte enablers, the bit support byte enable is set to 0. If the agent driver provides a separate response item through a put or the item down, then the bit provided responses should be set to 1 so that the register model knows that it has to wait for a response before converting it to register items. If this bit is set and the agent driver does not provide any response, sorry, if this bit is set and the agent driver does not provide any response, there are chances for simulation to hang. Since the APB control protocol does not support the slave responses, this set is set to 0. This is register predictor. The register model has different ways to update the model and keep its copies of the registers in sync with the value in DUT. By default, it updates the register model every time a read or a written transaction is performed. For example, if a value is written to the design using write method, it can easily update the mirrored value for that register in the model with the data written out. Similarly, when a read method gets the read data from the design, it can update and mirror the value accordingly. However, it is not required to always it is not required to use sorry. However, it is not required to always use the register model to write into the design, as the individual sequences with the address and data can be started on the same target agent to write into design register. This would make values in the register model stale and would require an update every time some other sequence reads or writes into the design. A component called predictor can be placed in a target bus agent interface to monitor for any transaction and update the register model accordingly. The UVM Leg Predictor component is a child class of UVM subscriber and has an analysis implementation port capable of receiving bus sequence items from the target monitor. It uses the register adapter to convert the incoming bus packet into generic register item and then looks up the address from the register map to find the correct register and update its contents. This is protocol independent and hence we don't need to define a custom class. However, we will have to create a parameterized version of a register predictor as shown below that can be integrated within our register environment. So steps to integrate a predictor. Declare the parameterized version of a register predictor with target bus transaction type. 2. Build the predictor in the register environment. And 3. Let's connect the register map, adapter, and analysis port to the predictor. Register environment integration. Let's use all the above components of integrate them in a separate register environment to make it more reusable. Okay, there are three components that we have to declare and create in a build phase. It's important to note that a register model has to be locked via invocation of the lock function in order to prevent any other test bench component or apart from the modifying the structure or adding registers to it. The build method of a register model is a custom function, not a part of the standard UVM library, simply to initiate building subblocks, maps, and register within the model. It's a good idea to place this model somewhere in the configuration database so that other components may access it. Now we have to provide the predictor with a mapping scheme so that it can match the address values of those of register in the model, and also have a handler to the adapter so that it can take the converted bus values directly. This is best done in the connect to phase method in shown above. Okay, next is connecting registers environment. Connecting registers environment. Till the previous stage, we have defined and created everything required within the register's environment. However, which agent is responsible for driving these register transactions hadn't been defined. Oh, only this. Okay, and then next is right complete example. The UVM register model example. In the previous few articles, we've seen what a register model is and how it can be used to access register in a given design. Let us see a complete example of how such a model can be written for a given design, how can it integrate it into the environment, how it can be used to write and read in design field. Design. The design has the following registers in the field that are accessible through an APB design. The design essentially represents a traffic light controller, which can be configured by writing into certain control registers. The control register contains a field to start a module and configure it to be a blink yellow or blink red mode. The state register is read-only and returns the current status of the design yellow, red, or green. The timer register stores the time in between the transition from each state. The profile bit allows the user to choose between the two programmed timer values. This can be useful for peak and off-peak of time. This is not a complete design since our purpose is to simply to show how registers in the design this design can be written, read can be read and written using a UVM register model. All the signals listed as a module ports belong to the APB specification. Interface. Let us declare an interface with the signals in the APB protocols, and this interface can be passed to the test bench as a virtual interface for the driver to drive some values to the design. To keep things simple, let us not declare clocking blocks and pod ports, although they are recommended in earlier project. The register model examples. A register model for the design registers discussed above can be developed as shown. In a typical project, this would be automated flow where scripts read register specification from a like IP exec and convert them into a register model. The register model can be directly plugged into a register environment or any other component as desired. So now next is the register environment. Now that the register model is available, next step is to connect all components required for the register model to work in a separate environment. This will enable the environment to be directly plugged into test bench and hide the connection between predictor, adapter, and register model from the top level environment. Since the adapter is dependent on the bus protocol in use, we need to drive a custom class from UVM reg adapter and let's name in a reg to APB adapter. The function reg to bus and bus to reg are defined here so that the register items are converted to APB bus packets and vice versa. The APB agent example. A AMBA APB is a bus protocol used for low bandwidth peripheral accesses, and a typical application of the protocol is in the access of control registers in a device. The code shown below is a simple model of the APB agent required for our purposes. It does not handle many of the features in an actual APB protocol. The test environment. Now that we have the register environment and the APB agent, we can create a top-level environment where these two can be placed and connected. Sequences. This sequence helps to bring the DUTO out of the set. It get the virtual interface handler from the UVM config DB, and it toggles the UV reset input directly from the sequence. Register accesses can be written inside a similar sequence, but for our purpose, let us simply call them from the test class. Test. The first part of creating a test library is to develop a base test that configures the test and the environment. Or other specific tests can be derived from this base test, so that it can focus on starting stimulus sequences. And quite, next is the UVM backdoor access. The UVM register backdoor access. UVM register model allowed access to the DUT registers using the front door, as we even seen before in the register environment. This means that all registers read and write operations in the environment are converted into transactions that can driven into bus interface of the design. Just like any other hardware component in a typical system would do, because these access are sent to a valid bus transactions, it consumed bus cycles. This is the recommended way to verify the register in any design, as it closely resembles with what happens in the design. What are backdoor accesses? UVM also allows backdoor accesses, which uses a simulator database to directly access the signal within the duty. Write operations deposit a value onto the signal, and the read operations sample the current value from the register signal. Since registers are leaf nodes in a digital system, depositing a new value in the middle of any design transition should not cause any problem. However, the control logic that becomes active during a typical bus write operation will not be active and hence any logic connected to this may not work as expected. A backdoor access takes zero simulation time since the HDL values are directly accessed and do not consume a bus transaction. This is not a recommended way to verify register accesses in any design, but under certain circumstances, backdoor access helps enhance the verification effort using front door mechanism. The defined backdoor HDL path. The simulator has to know the HDL path to signal for which it is trying to a backdoor operation. So it is responsible for a responsibility of the user to specify the signal path and the register model for every register or those registers which require backdoor access. To enhance the reuse and portability, the whole pathway is broken into multiple hierarchies. For example, the path given register can be split into the path from the test bench top to subsystem top level, and from subsystem to top to block level top, and block level top to the register block top, and finally register block top to the given register. If the system is reused in another design, only the section of the HDR path from the test bench top to the test subsystem top level needs to be updated. Example: we will add a HDR path to the traffic controller design examples seen in the front door access example, and perform the sum backdoor access write and read. HDR paths are added during register model construction. Basically, they are added to a certain function, and code hence can be done after later after register model construction. It's not uncommon to see an automated flow development by verification teams that parse the HDR path list provided by designer and then have information added to any existence register model. The most logical way to understand how it is arranged is by a top-down approach. First, look at the test bench level, then the duty level, then at any subsystem level if present, then any register block levels, and finally the registers. In our simple traffic controller design, registers are directly placed in the DUT, and hence hierarchy to access these signals are simple. Example of backdoor access in sequence. Okay, right. I think it's all we are finalized. Thank you for your time. See you next time.